Hello, welcome back to another episode of Math with Haas. So you are watching Precalculus Season 1, Episode 6. Season 1, if we recall, is on exponential and logarithm functions. And today we are going to begin with the following question. What is the inverse of an exponential function? So, I'm sure you've learned before about inverse functions in the context of polynomials. Like if you have a linear line, y equals mx plus b, to find the inverse, what you would do is switch the x and y. So you would have x equals my plus b, and then you would solve this new equation here in terms of y, and then that would be how you would find the new inverse. But the question is, how do we find the inverse of an exponential function? Exponential functions, if we recall, had this format here: y equals ab to the x. We could add a plus c if we want to include all of our transformations from the last video. So how do we find the inverse of that? Or more practical, why do we care about the inverse of an exponential function? Well, if we had something like, how about 12 equals 3 times 4 to the x plus 5, how would we solve and get that x down? Because we can subtract the 5 and divide the 3. So if we subtract the 5, we have 7 is equal to 3 times 4 to the x. And then if we divide that 3, we have 7/3 is equal to 4 to the x. But if we want to know what x is, we have to get it out of that exponent somehow. And to do that, I claim we need to know how to find the inverse of the exponential. So, what is an inverse function? In case you have forgotten, if we have y is equal to f of x, then the inverse says we are going to switch the x's and y's such that the inputs of the original function become the outputs, and the outputs of the original function are now the input. So we use a superscript here, -1, to denote that this is for the inverse. Okay, so the inverse function says that inputs and outputs are swapped. Alright, so when we think about y equals b to the x, we need to think about a function with the inputs and outputs swapped. Now I'm going to put a box around this because this is really the question. Now, how this is done is the logarithm. So I guess we'll stick with the logarithm. I'm going to use capital LOG for log. So if we wanted to replace, if we wanted the inverse function, we would write log base b of y is equal to x. So this function here in blue, you want to think of it as log base b of y equals x. That's how you want to say it. Okay, we want to make sure we have clear mathematical language. We need to be precise with our language so that when we communicate about math with others, we can have an effective dialogue. So this here in blue means log base b of y equals x. And this is how we're going to find the inverse function of the exponentials. So the logarithm, our first key point is that it is the inverse of an exponential. So let's go ahead and put that on here. So first main point, the log function is the inverse of the exponential function. And then this raises a second point. The exponential function is the inverse of the log function. And this just follows from the properties of inverses. So if we think about our inverse here, if we were to take the inverse and swap the inputs and outputs, you would actually get the original function back. Alright, so a key skill that you need to have when working with logarithms is rewriting. So we want to think about how can we rewrite exponentials as logs and vice versa. So we want to be able to convert from exponentials to logs and from logs to exponentials. So for example, if I had, how about a is equal to 5 to the y, we would rewrite this. So this right here is our exponential base, and that will be our logarithm base, so we would write that as log base 5. Now the output here is now the input, so that goes inside our log, and then our original input is now our output. So that'll be one way of rewriting. Another example would be if we have, say, 16 is equal to 2 to the 4th. That would be the same as log base 2 of 16 is equal to 4. Now, one way we want to interpret the logarithm function is we want to interpret the log function as giving the output as an exponent. So we want to interpret the log function as giving the output as an exponent needed to raise the base by in order to obtain the input. Failing at typing. There we go. Alright, so we want to interpret the log function as giving the output as an exponent needed to raise the base by in order to obtain the input. So if I were to plug 16 in log base 2, I get out 4. What that 4 says is that if I take 2 to the 4th, I should get 16. And in fact, that's what it is. You can use your calculator to verify, or you can just think 2 times 2 is 4, times 2 is 8, times 2 is 16. So think of the logarithm function as giving out exponent values, such that if you want to take a number and raise it to that power, you get whatever your input was. That's how we want to think about that. And let's see here, we did 2 examples of rewriting exponentials as logarithms, so we should rewrite a couple of logs into exponential. So let's go ahead and see a couple examples of that. So if I have log base 10 of 100, what does that even mean? Let's see. We should probably change that. We'll make that log base 10 of, okay, yeah, I know what I'm going to do. Is equal to 2. Log base 10 of 100 is equal to 2. We can rewrite that as an exponent, where we have our base 10 to our exponent 2 is equal to the 100 here. Alright. Now, the fact that exponentials and logarithms are inverses of each other give rise to these 2 very important properties. So, our first two properties of logs. So if we have log base b of an exponential, so notice the base of the log and the base of the exponent of the exponential function, they are the same. So if you plug an exponential of the same base into the log, what you will get out is just x. Similarly, if you have b to the log base b of x, you will just get out x. Let's go ahead and prove these now. So prove. So let's let about a equal b to the x. Okay, that means log base b of a is equal to x. Now, this is just by definition of rewriting the exponential as a logarithm. However, since a is equal to b to the x, I could substitute this term in for a. So then we get log base b of b to the x is equal to x. Done. And then for our second proof, it'll be something similar. Let's see, let's let a equal log base b of x. Then I guess we have b to the a is equal to x. Alright. But notice, since a is equal to log base b of x, we can take this whole thing and just plug it back in there. And for a, so you get b to the log base b of x is equal to x, end of proof. Alright, so we've verified our two properties of logs here. That's nice, easy little proofs. And these just follow directly from the fact that they are inverses of each other. Now, we can go ahead and make two more properties, but they really just follow from our first one here. That log base b of b to the x is equal to x. For example, if I plug in log base b of b, well, b is we can think of b here as being raised to the first power. We can put a 1 in there. So if we follow by this property here, this is going to equal 1 no matter what. So this is a useful way of thinking about logs. You think if the input matches the base, nothing else going on inside, then the output is just 1. Similarly, if we have log base b of 0, or not 0, we want log base b of 1. Well, this one's a little sneaky, but if we think about 1 as b to the 0, well, by our property here, then this is going to equal 0. So I know some textbooks will count these two here as also properties. I find this one useful because you think whenever you see a 1 inside a logarithm, that will be 0. So we could summarize our results as properties, quote unquote. So we have log base b of b to the x is equal to x. Then we have these two other properties that pretty much just follow. If you plug in a 1 into a log, you get 0. If you plug the same value as the base into a log, you get out 1. And then we have b to the log base b of x is equal to x. Now, these two properties here that I'm boxing in red will be very important for solving equations, exponential or logarithm, because these two properties tell us how to effectively undo logarithms or exponentials, and it's by using the opposite. So if you need to undo a logarithm, you use an exponential. if you need to undo an exponential, you use a logarithm here. And we will see that in future episode when we look at how to solve equations. For now, we'll just note that these two properties will be used heavily from now on. And in fact, they're just very useful in general. We'll make use of them even in calculus every once in a while. They're very useful. Alright. Let's see. Now, we must talk about some notation. So, I had previously wrote this here, log base 10 of some number. This here is actually bad notation. This needs to be, better notation is log of x. So we don't want to use this notation at all because it's just not proper notation. Log base 10 shows up quite often. It's very common. In fact, it is called the common logarithm. So let's put a name on this. I feel that looks spelled wrong. I guess we'll roll with it for now. Nope, it looks right. It is right. Alright, logarithm. Just a funny word. So the common logarithm here is always log base 10. So if you see a log that does not have a base on it, it is always log base 10. Never write this here because that is bad notation. Write this right here. Now, we saw previously this function y equals e to the x. Well, this has its own notation as well that its inverse does. So the equation y equals ln of x, that is the natural logarithm. So the natural logarithm is the same thing as log base e of x, where e again is Euler's number. However, this is bad notation right here, so never use it. You always want to use ln. And that is also what this ln button right here is. So look in our calculator, this ln button is natural log. This log button is log base 10. All scientific calculators, graphing calculators, have those as built-in functions. Let's see here. So I think we'll call that good for this video. We will continue with our discussion. We are by no means done talking about logarithms. We have 3 laws of logs to prove, and we have another important fact about logs, but that will require another video. So for now, I want to say thank you for watching this video. If you have been enjoying our content, please subscribe to our channel and support us on Patreon. Thank you for watching and joining our math party.